Indiana University East, Department of Science. Calculations involving strong bases. So, a strong base, what does it mean? A strong base, which is typically a group 1 or group 2 hydroxide, is a base that completely dissociates. This time it's dissociation, because they're on a compound, such that there's no NaOH left over. All you have is Na plus and OH minus here. And since they dissociate completely, the initial concentration of OH minus ions in the compound in the solution gives you the OH minus concentration. We do not need to worry about equilibrium. So here are some examples of calculations involving this. So let's look at the pH of a 1.3 molar sodium hydroxide solution. In this case, this is the chemical equation. Sodium hydroxide dissociates to form Na plus and OH minus. So for every mole of NaOH dissolved, you have 1 mole of OH minus. And so the molarity of the OH minus is equal to the molarity of NaOH initially, which is 1.3 molar based on the question prompt. Therefore, there's a couple ways you can do this. What I would do here is to figure out the POH, which is minus log to the base 10 of the OH minus concentration, which is minus 0.11. It's important that you keep the sign there. Therefore, my pH, you know that pH plus POH is 14 under 35 degrees C. So I rearrange it, pH is 14 minus POH, so I get 14.11. It is important to realize that your pH does not have to be between 0 and 14. It can be less negative, it can be negatives, or it can be greater than 14 under certain circumstances. So now, let's look at how we would calculate the pH of calcium hydroxide. Calcium hydroxide is the formula CaOH2. There are 2 hydroxide ions per formula unit of calcium hydroxide. So therefore, when dissolved in water, it dissociates to form Ca2 plus and 2 OH minus ions. Therefore, the number of moles of hydroxide ions is twice that of the number of moles of calcium hydroxide, and therefore the concentration of hydroxide ions in the solution is twice that of calcium hydroxide. Therefore, given that the molarity of calcium hydroxide is 0.0241 molar, the molarity of hydroxide is 0.0482 molar. Given this, we can use the approach of finding the POH to find the pH. As before, the POH is minus log to the base 10 of the OH minus concentration. Therefore, the POH is minus log to the base 10 of 0.0482 from here, and it's 1.317. Now, given this value of POH, we can use the formula pH plus POH is 14, and then pH is 14 minus POH. We're assuming it's at 25 degrees C here, and plugging in this value of POH, we find that the pH is 12.68. So, here we're given the pH of potassium hydroxide, and we need to find the concentration, the initial concentration of the solution. The POH, okay, so first we're going to find the POH here of the solution given the pH, and that's 14 minus the pH. So 14 minus 12.81, that's 1.19. Given this POH, we can then take the anti-log of minus 1.19. That will give us the concentration of OH minus, and that's 0.065 molar. Now let's look at the chemical equation for the dissociation of potassium hydroxide. So KOH becomes K plus and OH minus. So this is a 1-to-1 ratio between OH minus ions and KOH. And therefore, the concentration of KOH is equal to the concentration of OH minus which is 0.065 molar.